Okay, in this video, I'd like to do some exercises in which we use some of the identities that we established in the last lesson. And also, we're going to introduce some new identities towards the end of this video or in the next video. Now, in the last lesson, you had recorded your own, or I should say, you copied the identities from two videos that I found online that talked about these. Our textbook does a nice job of summarizing this information as well. Since you all likely don't have a physical copy of the textbook, I would recommend pausing the video now and taking a screenshot or copying this block down if you didn't already print it out from the handouts this week. But this block is what we would call our basic identities, our quotient identities, reciprocal identities, Pythagorean, and even odd identities. In the last video, these were called tangent and cotangent identities. I guess that's another name for them. I personally have always known them as the quotient identities. So here we go. I've got a few examples, and while the instructions say to simplify, I don't know if that's always the best phrase to use for this type of work. A better phrase would simply be to rewrite. The problem with saying simplify is that the end result when we're done here may not look more simple than what we started with. But usually, and I keep saying this, when we rewrite an expression, we do so with the hopes of making it more usable in a larger context. And without knowing what the larger problem is surrounding this particular component, you may feel a little bit lost along the way, but bear with us. This video and these examples are just meant to give you an opportunity to see how utilizing the identities work so that when we apply them in a larger context later, we won't be struggling with the process as much. So here's my hint for this first example. And that hint is to multiply by some form of 1 to change how an expression looks. In this case, I'm going to multiply this fraction by cosine theta plus 1 in both the top and the bottom of a fraction. Now, if you look at this fraction that I've just written in blue, certainly cosine theta plus 1 over cosine theta plus 1 would simplify to the number 1. And when that number 1 is multiplying by this expression, it's not going to change the value of that expression, but it will change the way that expression looks. Okay, and when we multiply these fractions together, we can distribute this sine into this group here, and what we would have is sine theta times cosine theta plus sine theta. Now, we'll see in a minute that that's probably not the best thing to do for this problem, but to walk through the entire process, it's okay that we do that. In the denominator, we have basically this binomial times another binomial, so we end up with cosine theta times cosine theta, which is also cosine squared theta. On the outside, we get a positive cosine theta times 1, then negative 1 times cosine theta, so minus cosine theta, and then at the end, minus 1 times positive 1, which is negative 1. Hopefully you'll notice that this plus cosine theta and minus cosine theta immediately cancel each other out, so we'll go ahead and do that. Nothing really evident stands out to me in the numerator or the denominator for that matter right now, so I'm just going to rewrite these and get a closer look at them. So I've got sine theta, cosine theta, plus sine theta in the numerator. In the denominator, we'll call this cosine squared minus 1. And for those of us that are brand new to trigonometric identities, you might be just scratching your head. So what's the big deal here? Why would we even do that? What good does that do? And what I would like to draw your attention to is this phrase here and this phrase here. So as you memorize your identities, certain ones are going to become a little bit more obvious. And for me, whenever I'm doing simplifying or rewriting of trigonometric functions, I'm always on the lookout for these cosine squareds or sine squareds. And in the back of my mind, I always wonder, is there some form of the Pythagorean identity that I can use to continue to rewrite that? And let's remind ourselves of one other thing here. We know that another way to write this might be cosine squared theta is equal to 1 minus sine squared theta if we had moved this sine squared to the right side of that equal sign. And so what this is telling me is that anytime I see a plain old cosine squared theta, I can actually replace it with this expression here because they are equivalent. And I do see a cosine squared theta over here. So I'm going to replace that. I'm going to change it to 1 minus sine squared. So let's copy the numerator, sine theta cosine theta plus sine theta. And in the denominator, I'm changing this cosine squared to 1 minus sine squared because that's what our identities have said. Cosine squared is the same as 1 minus sine squared. So I've made that change. Cosine squared is now 1 minus cosine squared, and we've got a minus 1 here. Now this 1 will cancel with this minus 1, and we now have sine squared in the denominator, although it's a negative sine squared because of that subtraction sign. Now here's where going back to the original form before we distributed of this numerator might be more helpful. I'm going to factor out sine of theta from both of these two terms, this one and this one. And if I factor out sine theta, it moves to the front of a grouping symbol, and we have sine theta times cosine theta plus 1. And why that's helpful is because of this. If I rewrite sine squared or negative sine squared as negative sine times sine, you'll notice that this sine theta in the numerator can factor out this sine theta in the denominator. And what we have left over is this phrase, cosine theta plus 1 over negative sine theta, because this negative sign didn't disappear. Now here again, that didn't make this equation more simple in my opinion. This is not any more simple than what we saw above, but again, perhaps this expression was inside a larger equation that we were working with, and rewriting this expression into this form might be more beneficial. Maybe there's a product or a quotient that would really benefit from having a denominator of a sine value instead of some form of cosine like we had prior. I don't know. But for right now, this is just, again, an example of a way to rewrite the original expression using trig identities. Now, number 2 here is a little bit more, well, it's a little bit nicer in that this will simplify to something a bit smaller than what we're starting with. So let's go ahead and jump in here. And one hint that I'd like to provide this time is rewrite in terms of sine or cosine. In the first example, we said that with fractions, sometimes multiplying by some sort of 1 to change the way an expression looks might be helpful. In this case, when we've got several trig functions floating around, it's a good idea to take these trig functions, or secant and cosecant, try to rewrite them in terms of sine and cosine. This gives us a more consistent trigonometric function to work with. And so, using our definitions of tangent, or our quotient identities, we know that tangent can be rewritten as sine over cosine, and cotangent can be written as cosine over sine. Now that's going to introduce fractions here, but we can handle that. So the sine theta stays alone, and then tangent gets written as sine over cosine plus cosine over sine. And from here, we've got a couple options, and you'll find that when working with trigonometric identities, there's not always a clear path to follow, and that's, I think, what gives most students trouble with this new content. But since there are multiple pathways, the nice thing is what you do at first. If it doesn't work, you can try another direction, and hopefully it does. So with a little bit of practice and tenacity and persistence, you'll ultimately find your way. Rather than worrying about these fractions on the interior, I'm actually going to distribute this sign into the grouping symbol. And this sine function out front is kind of like a sine over 1. So when it does distribute, this multiplication occurs only in the numerator. So I'm left with sine squared over cosine plus sine theta times cosine theta over sine theta. And at this point, you might recognize that sine theta will cancel with sine theta. And now we're left with sine squared over cosine plus cosine theta. And I'm going to leave this over 1 because what I notice is that I can actually create a common denominator here. If I multiply by 1 using that first hint of the video, this time it's cosine over cosine, this is going to create a common denominator of cosine theta in the denominator. And in the numerator, I'll now have cosine squared. And hopefully you're recognizing at this point that I'm leading up towards a Pythagorean identity here. I've got sine squared and cosine squared. With a common denominator, we can actually, and I'm going to erase this, I'm going to actually rewrite this as a single fraction. Now that we have a common denominator, we have sine squared plus cosine squared over the denominator cosine theta. Rather than having two fractions, I've just combined them into one. That's the benefit of having a common denominator. And now again, this is what I was angling towards. Here's that Pythagorean identity coming back into play. This time I see sine squared plus cosine squared. And the really nice thing is that sine squared plus cosine squared, according to the Pythagorean identity, is equal to 1. So this entire numerator is really just the same as the number 1. And we have 1 over cosine theta. And I would argue that this is much more simple than what we started with. I've got a fraction with a single trig function instead of 3 different trig functions. But I would also argue, too, that there's one more identity we can't forget about, and that's that 1 over cosine theta is really equal to just secant of theta. So I'm going to rewrite this last expression down here as secant theta. And so as it turns out, what we started with, this original expression way back here, with a little bit of algebra along the way, has turned into a much more simplified form down here. So sine of some angle measure times tangent of that angle measure plus cotangent of the same angle measure, that expression would be exactly the same as simply evaluating the expression secant of that angle measure. And here's where the simplification name comes into play. We truly did simplify this expression into something a bit more usable. I'm going to run through these last two examples a bit more quickly here and with a little bit less commentary. For number 3, I'm simply going to FOIL this pair of expressions. So after foiling, I get a result that looks like this, and the two middle terms will cancel themselves out. So after we combine like terms, we're left with 1 minus cosine squared. Here again, with more practice, you'll recognize that 1 minus cosine squared is actually quite handy because, again, if sine squared plus cosine squared is equal to 1, then by moving cosine squared to the right side by subtracting, we know that sine squared is equal to 1 minus cosine squared. And this is exactly what we have in our simplification down below. So 1 minus cosine squared, after using our Pythagorean identity, is simply sine squared of theta. So once again, this expression that we started with, while it didn't appear too complicated, has been simplified into something a bit more manageable. It's much more smaller and condensed. With number 14, I don't know, I'm sorry, with number 4, I don't know that we will simplify this into something smaller, but there are some neat tricks that we can employ here to rewrite this in different terms. So what I'm going to do first is rewrite this cosine squared into some form of sine squared so that we have only sine squared in the expression. Okay, so cosine squared using the Pythagorean identities is the same as 1 minus sine squared. Now I'm going to distribute in this grouping on the left. And since we have 19 minus 19 sine squared plus 20 sine squared, well, we can combine like terms. Negative 19 sine squared plus 20 sine squared is just sine squared. So we're now left with 19 plus sine squared theta. And that's one way to rewrite this expression. Certainly we've condensed it and we've rewritten it into a nicer form. So what if you were thinking, well, I'd like to rewrite sine squared as cosine squared? Well, certainly you could do that too. And again, distribute, this time in the right-hand group. But when you combine like terms this time, 19 cosine squared minus 20 cosine squared, well, that's a negative cosine squared, and we're left with 20 minus cosine squared. And this expression doesn't really match this expression that we ended up with over here. Or does it? Think about this for just a second. We know that cosine squared is also the same as 1 minus sine squared. So if I substitute 1 minus sine squared in place of cosine squared, we would have this expression. And now 20 minus 1 is 19. And when you subtract a negative sine squared, that's the same as a positive sine squared. And if we were just to take this a little bit farther now, we've got an expression that matches. This is a good thing because now this is our way of saying it doesn't matter which direction you chose, whether you started with this trigonometric identity in that process or this one over here, you can and will end up in the same spot. And to make this connection go a little bit further, let's try that with the other side here. We now have sine squared, which we know is the same as 1 minus cosine squared. So 19 plus 1 is 20, and when you add a negative cosine, that's the same as minus cosine squared in this case, and certainly 20 minus cosine squared is the same as 20 minus cosine squared that we had back here. So either method is perfectly fine, and both methods do create a simplified result. So there is a little bit of an exercise in using trigonometric identities to rewrite expressions and simplify expressions. I'm going to stop this video here since we're running quite long, and I'm going to create another video to talk about the sum and difference identities down below.